So today we're going to have a little fun. We're going to experiment with a more complex digital circuit and think about different ways of implementing it that achieve different goals. So as an engineer, when you're designing something, particularly a digital system, your customer may have different ideas about what it is they want it to be, to achieve. Performance always seems to loom large. And in fact, for many years, sort of digital systems, computers, for example, the main goal was to build them faster and faster and faster. And even though we always have a need for speed, nowadays we start being concerned like, will it run all day on a battery? So power starts to be a consideration. And then finally, there's size. And so obviously, if you need 18 chips to implement something and your competitor manages to squeeze it all onto one integrated circuit because they've been much cleverer about the circuit, you can implement things. You can be very competitive by dealing with size. And I'll show you an example of that a little later in this lecture. Okay, so the problem we're going to work on, sort of as our stalking horse, is binary multiplication. So we're going to have two unsigned operands, each of n bits. And if we take two n-bit numbers, unsigned numbers, and we multiply them together, we will get a 2 n-bit product. In other words, the product will be twice as large as the two operands. And when the two operands are the same size. And we can sort of see here, if you just do some mental arithmetic about taking sort of the two largest unsigned binary numbers and you multiply them together, and you can sort of figure out what the numeric size of the product, and then you can sort of see that we're going to need 2 n bits to fit in all the possible results that we get. So that's the problem we're going to work on. It turns out that for small multipliers, like even a 1-by-1 multiplier, the hardware isn't too bad. Puzzling a little bit over how to build a 32-bit by 32-bit multiplier, you quickly come to the realization that that's a lot of hardware. I mean, there's lots of partial products to create and lots of adders needed to add them together, and your fingers are getting shorter as you type them in. And it can pay to think a little bit about the problem and find out if there's a way of structuring it so that we can build building blocks and then perhaps use the building blocks to actually assemble the final unit. We may end up with much less total work, even though we'll create the same amount of hardware. We'll do it in a structured way where we'll let sort of reuse of a basic building block stand in for just typing a lot of hardware in gate by gate by gate. Okay. So the first thing we're going to do is to spend some time thinking about the structure of multiplication and see if there's some way of dealing with multiplication that allows us to say, oh, I can decompose a big problem into a collection of smaller problems. And if I can do that, then I have a way of, I can try to make myself a set of tinker toys that I can sort of plug together in a hierarchical fashion. So let's suppose that we have n-bit by n-bit multipliers here. So we have something that will take two operands A and B and produce this 2 n-bit result. So let's just, for the sake of argument, say those are what's in your toolbox. And now somebody comes and asks you, can you solve a problem with twice the size? In other words, if I start off with 2 n-bit operands, which will produce a 4 n-bit result, is there a way of thinking about the problem that allows me to use the building block I actually have been able to check out from the stockroom? And in fact, there is, and you're of course quite familiar how to do big multiplications using just that little multiplication table that you learned a long time ago. And the way you do it is you decompose the problem where you're sort of taking 1 digit at a time down here and 1 digit at a time down there, and doing a table lookup in your head to say 7 times 5 is 35, so I write down 5, carry the 3, so forth and so on. So slightly more abstractly, what we can do is to break down. So each of these A's and B's down here can be thought of as really 2 n-bit numbers concatenated. There's the low half, and then there's the high half of the number, each of which is n bits large. So each of these little squares here represents one of the n-bit operands that we already know how to deal with. And this is a diagram that shows us how to break the 2n times 2n multiplication into a series of sort of, block by block. You can, if you thought of each of these guys as, if you will, a digit, the thing that we can deal with, the thing that we know how to implement. In our case, it's the multiplication table, but in this case, it's n-bit multiplication. You can see we can parlay that skill of being able to do an n by n multiply by basically breaking this big problem down into 4 subproblems, which will create these 4 partial products. And so one way to think about this is I can use 4 copies of this building block to deal with the A low and B low and A high and B high operands as n-bit operands. And then I'd simply have to worry a little bit about the appropriate scaling, moving things over. So think of this as, this partial product is shifted over by n bits. It's like multiplying it by 2 to the n. And you do that quite naturally when you do multiplication. Each partial product, as you move across the bottom row doing your multiplication, you're carefully shifting these partial products over by 1 column, representing that, the fact that one of the operands which you dealt with as a digit is really some digit times some number of powers of 10. And then when you write down the partial product, you shift that partial product over by that number of powers of 10. And it's now it all lined up just the way it should. So I don't need to reprise multiplication for you. But this is just sort of a diagram that shows how to break a big multiplication problem into a series of small multiplication problems. So what we're going to do is say, okay, that I understand the structural principle. Let's actually roll up our sleeves and fool a little bit with the actual hardware. So if we're going to start our basis, we could start with sort of a 1-by-1 multiplier. And if we think about the 1-bit multiplication table, we build a little truth table like the one you see over here on the right-hand side. And you look at that and say, well, 0 times 0 is 1. In fact, 0 times anything is always 0. And then the only interesting entry in the table is the 1 times 1 entry, which produces a 1. So you say, okay, that's the truth table for a 1-by-1 multiplication, which, of course, as our friend noticed, is actually just the truth table for an AND gate. So it turns out that doing a 1-by-1 multiply is not terribly complicated in the world of binary arithmetic. We can implement the multiplication using a single AND gate. And it produces, well, in this case, we only get a 1-bit result, but in general, when you multiply 2 operands of a certain size, you produce a result which is twice the size. And the reason why this little special case rears its head is because of the special properties of multiplication by 0. Everybody else would have, multiplying by bigger numbers tends to produce the 2 n-bit results. We just don't happen to see that in this table. Of course, you can say, well, that's a very simple basis. And as we'll see, starting here will get the point across, but we'll look at some of the hardware that we're creating and say, that doesn't seem as efficient as I would hope. Couldn't we do a better job? And the answer is almost certainly. And in fact, if we start with building blocks that are slightly more complicated, like a 2-bit by 2-bit multiplier, all the same structural story that we're going to tell works just fine, but we'll use gates a little bit more efficiently.